Alright, so section 7.6 is on what's called a common logarithm, and that means a logarithm with a base of 10. So in general, if you ever see a problem where they just say the log of something, like the log of x, and they don't actually write a base right here, it's assumed that the base is 10. That's why it's called a common logarithm. So a couple of things we want to do in this section. First, show you how to find them on a calculator, and then solve exponential equations by using logarithms, also solve inequalities, and then something at the end called the change of base formula. Okay, so first of all, there's a button on the calculator that usually says log, and I'll show you where to find that. And that's how you find logarithms. So we'll do a couple of these. Let's do the first two, the log base 10 of 5 and the log base 10 of 0.3. Okay, so here is the button on the calculator. The log button is right on the left side that just lit up in red like that. And we wanted to find the log of 5, and it's this number, so let's test that. Let's raise 10 to that power. So 10 raised to the second answer, which is right near that minus sign, and press equals, and we do get 5. That's a way to test that we did it correct. What was the other one? Log base 10 of 0.3. So let's do that. So the log base 10 of 0.3, and that is going to equal negative, so 10 to the negative power right there. Remember, raising to a negative exponent means flipping and making it positive. So this should give us 0.3, and it does. Okay, you could also do it by going to math and then scrolling all the way down to log base. And just to prove it to you, let's do the log base 10 of 5. We should get the same 0.698 answer, and we do. So that just shows you the calculator assumes that log means log base 10. Okay, a couple properties to be aware of when we're talking about logs, or logs of different powers, and particularly powers of base 10. So first of all, this right here, the log base 10 of x, that's another way of saying 10 to some unknown power is equal to x. Okay, this right here, the log base 10 of 1, 10 raised to what power equals 1? That's going to be 10 to the 0 power equals 1, so that equals 0. The log base 10 of itself, what power do you have to raise 10 to get 10? You have to raise it to the first power. 10 to the first power equals 10. And then finally, the log base 10 of 10 to the m, what power do you have to raise 10 to get 10 raised to that power? You have to raise it to the m power. 10 to the m is equal to that right there, 10 to the m. Just a couple properties to kind of show you how those work. Alright, so obviously most of the time that you use logarithms would be, there's many real world scenarios. We talked about the Richter scale and tornadoes. This is another example. Decibel levels, that refers to sound. So the loudness L in decibels of a sound is given by this equation. Okay, L is equal to 10 times the logarithm, and this is the log base 10, even though they don't write it there, of the intensity of the sound, which is I, over the minimum intensity detectable by the human ear. Okay, it says residents living several miles from a concert venue can hear the music at an intensity of 66.6. Okay, so that means this number right here is 66.6. So let's plug that in right here. Intensity, I stands for, right here, the intensity of the sound. They're telling us the intensity of the sound is that many decibels, 66.6. How many times the minimum intensity of sound detectable by the human ear was the sound if m is defined to be 1? Okay, so we are, actually I'm sorry, let me say that I did this slightly wrong here. So I is the intensity of the sound, and they're asking us, they're essentially asking us what that is. The L value is the loudness of the sound, and that's a little bit confusing how they worded that. So this number 66.6 is how loud the sound that they're hearing is. We don't know the intensity of the sound, that's what we're trying to find. And they're telling us m, this number is equal to 1. Okay, so I over 1, that's the same thing as I. So I'll just write it as I. What we're trying to find is the intensity, so I. Alright, so first of all, let's get rid of this 10 right here by dividing by the 10. And when we divide this by 10, we get 6.66. This book seems to like using that number a lot for some reason, I'm not sure why. the log base 10 of I. Now we want to change this to exponent form, so this number raised to that power equals that answer. So 10 to this number is equal to the intensity of that sound, and whatever that turns out to be, 10 to the 6.66, that's going to be the how many times the minimum intensity of sound. So it looks like quite a large number. So let's test that. 10 to the 6.66, and it is 4,570,881 times the smallest sound that people can hear is the sound at that rock concert. So that's quite loud. Alright, now how do you solve, in general, how do you solve equations using logarithms? So this is why I wrote this right here. Don't divide by 4, it's not 4x. Here's the wrong way to do this. And I'll show you with an easier example here. Let's do this. Let's do 2 to the x equals 8. And then over here we'll solve this equation, 2x equals 8. So on the right we know that we have to divide this by 2, and we get x is equal to 4, and that makes sense. 2 times 4 equals 8, so easy to check. The way that most people do this is they wrongly divide this by 2, and they say, well, those cancel, and x equals 8 divided by 2 is 4. That's clearly wrong, and here's how you can see that that's wrong. 2 to the 4th does not equal 8. If you took 4 and you plugged it in here, that's wrong. Okay, so the cardinal rule in algebra is you see what's being done to x and you do the opposite. The opposite of multiplying right here would be dividing. That's why I divided. The opposite of raising to a power is not dividing. Okay, the opposite of raising to an exponent is taking the logarithm. So that's what we have to do for these. Okay, so we're going to take the logarithm of both sides. And it's usually, it doesn't matter what log you take, but because we're taking, yeah, actually, you know what? Let's just take the log base 10. I was going to say we could take any log base, but it's, since we're talking about the common log, let's take the log base 10. So the log base 10 of 4x equals the log base 10 of 19. And remember from an earlier section, when you're taking the log and you have something raised to a power, you can take that and slide it in front. And this is important. You can only do that when you're taking the log. Like, you can't have 4 to the x and just for no reason at all slide the x in front. That doesn't work. You have to be taking the log in order to do that. So we are taking the log here, so now we can put that in front. Why are we doing this? Because we're trying to isolate the x. We're trying to solve for x, and we can't solve for it when it's up here as an exponent. Now we can. X is being multiplied by that, so the opposite of multiplying would be dividing. And then we divide both sides. We're going to get this as our answer for x. And it says round to the nearest 10,000th. That means 4 decimal places. So we'll put log 19 divided by log 4 in the calculator. So log of 19. It's important to close that parentheses, otherwise it's not going to give you the right answer. Divided by log 4. So 2.1240 if we round to 4 decimal places. And it'll be easy to check that. Let's raise 4 to that power and see that we get 19. And we do, so that's how you can check. Alright, let's do one more of these. Let's do number 3b right here. So same thing, we do not want to divide by 6. 42 divided by 6 is 7, but 6 to the 7th is clearly not 42. It's a much bigger number than that. 6 to the 7th would be like 279,336, I think is a huge number. So what we want to do is take the log of both sides, and now that we've taken the log, only at this point can we take that and slide it in front. We can't do that unless we're taking the log. Okay, and then we're going to divide both sides by log of 6, because that's what's going to cancel out the thing that's attached to the x. This number right here will be x, and it turns out to be 2.0860. Okay, slightly more complicated problem now, and if this is confusing to you, then just take a look at this and replace it with the letter. So pretend that that whole thing right there was the letter A. So you have 10a plus 2 equals a 14. And you know how to solve that. It's not difficult. You would subtract 2 from both sides, and then you would finish by dividing by 10. So it's the same thing that we have to do here. We can't do that log technique that we just talked about until we clear away everything around it. So we start from the outside most thing, which is this plus 2, and we would subtract that. So we're going to get 10 times this thing right here. I'm going to put that in parentheses just so we can have it look a little bit better. So 14 divided, or minus 2 would be 12. Now we divide by 2. Or sorry, divide by 10. So we would get 12 to the negative 4x minus 9. And 12 divided by 10 is 1.2. Now at this point we need to get the x to come down from where it is. And the way that we can do that is by taking the log of both sides. So I'll take the log of this. I have to take the log of both sides. Whatever I do to one side is done to the other. Now this is a part where people tend to make mistakes. We're going to take this whole thing and slide it in front. Here's where most people make the mistake. They say negative 4x minus 9 times the log of 12, and that is wrong. And I'll tell you why it's wrong. Okay, it's wrong because right now you're only multiplying this 9 by the log of 12. And in reality you took this entire thing. So you need to multiply that entire thing. And the way that you signify that is you put a parenthesis around that. Now that entire parenthesis is getting multiplied by log 12 instead of just the 9. So let's get rid of this by dividing log 12 on both sides. So we have log 1.2 over log 12. So this will now simplify to negative 4x minus 9 is equal to whatever this number is. And I don't recommend finding what that number is till the very end. You don't want to round answers till the very end of the problem. Otherwise you'll start getting inaccuracies. So we would add 9 to both sides, and then finally we would divide this by negative 4 and divide this whole thing by negative 4. So let me show you how to put this whole thing in the calculator correctly. You have those logs, and then you have to add 9, and then you have to divide by negative 4. So you can do that in a couple steps. If you want to do it in one step, here's what you do. Make a huge outer parentheses, okay, and then see if I can do this kind of split screen to show you a little bit better. There we go. So on the right, encircled in red is what we're trying to do. So you want to do, actually I don't know if this is going to work. Let's see if we can get it from this side. There we go. So it might work slightly. So we want to do the log of 1.2. So I'll make another parentheses here. The log of 1.2, close that parentheses, divided by the log of 12, close that parentheses, okay, and then I want to take that number right there and add 9 to it, okay, and then I want to take that whole thing and divide it by negative 4. So I would really recommend doing this in a couple steps, but that will at least, this number here is going to give us the top part equals that, and then I'm going to divide that by negative 4. It's easier to split it up because if you do it in one step there's a likelihood of getting a mistake. So rounded to the nearest 10,000, the answer is negative 2.2683, and you could take that and plug it in for x at the top up here, okay, and you solve that out and you would end up having it equal 14. That's an easy way to check. Let's see. Okay, the last thing I want to show you is inequalities. So the thing that they're saying here is to remember that if you're multiplying or dividing each side by a negative number, you have to switch the sign. Okay? So we'll have to be aware of that. For example, if you're doing negative 3x is greater than 9, since I'm dividing by negative 3, this sign right here would change direction. The x is less than negative 3. So the same rule applies with logarithms. Okay. Alright, in this case we're taking the log of both sides. That's not multiplying or dividing by a negative number, so we don't need to switch any signs. So we'll do the log of 3 to the 5y is less than the log of 7 to the y minus 2. The property says that as long as we've taken a log, we can take these and swing it in front. So we have 5y times the log of 3, and that is less than, remember here we don't want to write y minus 2 log 7. This is wrong because we're only multiplying the 2. We want to multiply the whole thing, just like that. Okay, now what we need to do is, it would be a good idea to distribute that y minus 2, because otherwise we don't want to divide by y minus 2 at this point, then we're not sure if we're dividing by a positive or negative number. So we'll distribute to this thing, so we get y log 7 minus 2 log 7. And that is less than this thing. Okay, now what we want to do is get all of the y's together on the same side. Okay, and the easiest way to do that, of course, would be to just subtract this term right here, because that has a y in it, so we want it to be on this side. Okay, so we will have 5y log 3 minus y log 7. This looks confusing because of all these logarithms here. By the way, that's a negative 2 log 7. This looks confusing, but keep in mind these are like numbers. Log 7, if you put that in a calculator, it's a number. It's like 0.8 or 0.9. So that's like, this is almost like saying, 7y minus 0.8y or something like that. So it's not meant to be all that imposing. Okay, now these have a common factor. You don't have to do it this way. You could plug these numbers. You could plug 5 times log 3 and log 7 into a calculator and do it that way if you prefer. But another way you could do this is these both have a y in them, so let's pull out a y. And if you pull out a y from this term right here, you would get 5 log of 3. Pull out a y from this term, you would get log of 7. And then we have this term right here. Okay, we want to solve for y, so we're going to divide by this thing right here. And here's where you might have to change the sign. If this thing here, if that's a negative number, we would have to change this sign. Okay, it turns out that if you plug that in a calculator, it's not a negative number, so you don't have to do that. So here's our final answer. Our final answer is going to be y is less than this thing right here. And let's plug that in a calculator to see what it should equal. So negative 2 log 7. Here is our answer. Negative 2 times the logarithm of 7 equals that. And then we're going to divide that by this whole thing in parentheses, this bottom part right here. So divide that answer by 5 times the logarithm of 3 minus the logarithm of 7. Okay, and let's make sure we close all our parentheses there, and we get negative 1.09. And you might say, well, that's a negative number. That's true, but the bottom part that we divided by is positive. Okay, remember this was a negative number here. We're dividing by something positive, so it should be a negative, and its y is less than negative 1.0972. That's our final result. Okay, last thing I want to mention is something called the change of base formula. And the change of base formula basically says this. It says if you have the log, let's say the log base 3 of 8, you could put this in a calculator. Most calculators have a button where they give you an option to put the base in, but suppose you didn't have one. You could do that by doing the log of this big number divided by the log of this small number right here. These two things are equivalent. And that's actually what they show you right here. That's the same as taking the log base 10 of this number divided by the log base 10 of that number right there. Okay, there is a proof for this, and we'll show you what that is right here. So let's suppose that we call x this expression right here, the log base a of some number n, and we're going to say let's call that x. We change that to exponent form. A to the x power would equal n, so that's where this comes from. Let's take the log of both sides, and let's take the log with a different base, because we're trying to prove something called the change of base formula. So we'll take the log base b of this side and the log base b of that side, and we get this right here. Now we know that there's a property that says we can take this and swing it in front right there. So we get x times the log base b of a, still equal to that left side right here. Let's solve that for x. Let's divide both sides by the log base b of a. Log base b of a, so those cancel. So we're left with x equaling this right here. X is equal to the log base b of n over the log base b of a. But what did x equal? Up here we said that x equals this thing. So let's replace that. That means x is equal to this. And it also equals this right here. And that's the proof of the change of base formula. It basically says if you have the log base a of n, that's like taking the log of this divided by the log of this right here. So there is the proof. Let's actually apply it to some examples. Express that in terms of common logarithms. So that's going to be the log base 10 of this number divided by the log base 10 of this number. And then round that answer to the nearest 10,000. So I'm going to show you that this works both ways. Let's do the log of 20 divided by the log of 3 first. So the log of 20, oops, log of 20 divided by log of 3. And remember, even though it doesn't say that there, that's the calculator is doing the log base 10. So we know the answer is 2.72. Now let me show you how to do it with the actual log button. Okay, let's prove that these are the same numbers. So the log base 3 of 20 should be the same answer that we just got right there, and it is. That's the change of base formula. So that is section 7.6 on common logarithms.